Aston Martin recently launched its AMR23, and while the livery is almost the same as last year's, there's a lot of really interesting aero work that has changed. In this video, we're going to go from front to the back of the car, looking at all the new aero details and how they work. For those of you that are new to my channel, I was an aerodynamicist for Mercedes for the 2018, 19 and 20 Formula 1 seasons, and I now work as an aerodynamics consultant, designing race car aerodynamics kits for cars in all different classes all around the world. Now, a lot of the items on this car are a bit of a carryover and evolution from last year's car, but there's also some really cool stuff around the Sidepods where they've taken slightly different directions to other teams and sort of combined a few different approaches into something that I think is quite neat. Before we get into the analysis, I'm going to put my standard disclaimer of Formula 1 car aeroflows are very complicated and you can't predict them 100% accurately by eye. You need CFD or wind tunnel for that. Starting with the front wing, I've got a little bit of a comparison for you. Over here, what we have is last year's front wing. This is the sort of standard one that they launched with, and I would kind of call this their season average wing. Down the bottom, I have here what they ran at low balance. So I believe this particular picture is from Paul Ricard, and this is their sort of lower downforce-ish front wing. And this is, of course, the front wing that they just launched with. What you'll see is that it's moved far more towards this lower balance style and away from their launch style wing. You can see that this inboard portion that was still cranked on that style of wing has been more backed off. So it's got this backed off inboard portion, then rises up to this quite aggressive portion just inboard of the tyre and then slopes down quite a lot, which is much more similar to the low balance wing, where you can see that they're fairly low through this particular portion and they crank to this region and drops off. So this outboard portion of the low balance wing is very similar to what they just launched with. The inboard portion, they've actually got it slightly more cranked on this launch variant. You can see that this is less of a drop off than this particular variant here. So why would they be shifting to this particular design? Well, there's a few factors at play. One is that they are now connected on the first element of the wing. You can see that the old wing ran that very popular style last year of detaching the first element. More and more cars this year seem to be going to connecting the first element into the nose. Now, as this decreases the porosity in this region, the chance is that the new wing generates a little bit more load and a little bit more suction along its centerline than the older wing. So you've got one factor going on there. Another option here is that what they've actually launched with here is their lower balance wing. That is on the table. It's more likely, I think, that they've changed it aerodynamically, but it is possible that what we've seen is in fact their low balance wing. The other option is that this particular wing, they took a lot of the learnings from this low balance wing, found that it had some beneficial aspects, maybe in terms of the wake management of the tire or the squirt management of the tire, or maybe it had a beneficial aspect in terms of downwash along the floor. So obviously if you bring this portion down, you're going to get more downwash on this inboard portion along here. So you'll get more rotation this way. Maybe that was beneficial for the floor further downstream, loading up that forward floor leading edge. So maybe they wanted to extend that downwash region, whereas with this wing, the downwash region wouldn't be so much air, it would be more coming down in this particular bit and this particular bit. So maybe that looked quite beneficial, and they've actually been able to work out how to make that work for their prime wing. And to make sure that they've got quite enough load, they've just done that tiny little bit of that extension of this region, making that curve that tiny bit bigger, and also cranking up that flap as hard as they can go. They also, like I have been speculating with some of the other cars, could have found a little bit more balance in the forward floor, or maybe they've lost a little balance from the rearwards floor. An interesting detail to just note on this front wing is that on the inboard portion of the second element, it's actually been quite fattened up on the top surface. You can see how thick this is and how bulbous. This isn't usually how we would specifically design an aerodynamic profile. So what I'd assume is that a lot of this thickening in this region is structural to make it a little bit more structurally efficient and increase the bending strength of this region of the wing. Now, even though this is a structural element, it does have some aerodynamic ramifications. Obviously, pumping up the top surface here will increase the downwash in this region, and even though it looks like they curve back a bit, you can see that they've had to back off this region here and this region here have both been fairly backed off. Now, backing this off will help clean up the junction losses in between there and obviously will help deal with any additional downwash caused by this structural thickening. The other main changes can be seen out towards the end plate, where what you'll see is that the old car had basically a square up and down trailing edge on the end plate. It still had the same sort of angled sweep on the top as the new car, but the new car has this cutaway style at the rear. Now this is very similar to what we saw on the Alfa Romeo. And you can see how visually from the side this exposes the wing elements back here and here, and this should improve the amount of outwash that's coming across from the high pressure region on top of the wing. We should have a bit of high pressure there, and that should drive a little bit of outwash. And you should increase the circulation around this rearwards portion because obviously there's suction underneath the wing, there's pressure on top, and we're cutting away a bit of the end plate, so we should get more outwash up high and more circulation. The other thing you'll note is that the chord lengths of the elements of the wing at the tip are a little bit more even now. Previously, the first and the second element were quite similar in length, but the rear elements are now shorter, and you can see that previously they had a huge amount of downwash from that particular corner right at the rear. I'd imagine that this is just an indication that they don't require such an extreme level of downwash from that particular portion anymore. Maybe this feeds into cutting away the end plate here has achieved a lot of that intent without you needing that particular geometry. Looking further rearwards, you can see that they've ditched that Red Bull style double barge board geometry that they were running with, and they've gone back to a conventional single barge board. It looks like this is more or less pushed forwards towards the limits of legality, but there is a little detail of interest with respect to this junction with the top floor, and I'll show you from the front what it looks like. You can see that there's only a very small rise from the floor up to the top of this particular barge board element. Now, that is a bit of an indication that the floor out here must be quite high, because when you look from the side, the barge board looks like it must be more or less at the top of the legality box. So this outboard floor section looks quite high, and conversely, when you look from behind, the inboard floor section looks relatively low. In fact, it looks like the inboard floor section might actually be lower than the outboard floor section. So why would they want to do this? Why would they want to lift this floor edge up? Well, when you lift this particular portion of the floor edge up, you increase the pressure in this particular region here compared to where it was before. And what we have going on underneath is that we obviously have our inner turning vanes going along here, and they go back there. And we've got our barge board on the outside. Now the barge board is going to be casting off a vortex underneath it, and the turning vanes will also have their own vortices underneath it. Now the turning vane vortices, the forward portion of the vorticity on those will most likely get drawn into the main floor vortex system, which is quite critical for ensuring maximum downforce through the tunnels, whereas I would hazard a guess that the barge board vortex is somewhat less critical. And the barge board floor vortex probably actually has a really big pressure differential across it, because we've got a lot of pressure on the outside of here, we've probably got some suction underneath here, so we're going to end up with a floor vortex that's probably a little bit messy and probably doesn't have a huge amount of utility. So when we lift up this outboard floor portion, what we do is we pressurize this floor, like I said, and that will decrease the pressure differential across the barge board shedding edge down the bottom. When you decrease that pressure differential, what will happen is that the vortex strength will decrease. And like I hypothesized last year, I thought that maybe with the Red Bull double barge boards, they might have been getting it so that the vortex was shedding the other way out the bottom of this barge board. But if you lift this floor leading edge, you should be able to achieve a lot of that effect of weakening this particular vortex. Now, this will obviously support the barge board. This will weaken the strength of the vortex, clean the vortex, so it will probably clean up the flow further downstream. And it will also produce a lot of stagnation pressure in this region here, which should help force the tire wake further outboard. The other thing that it will do is it will increase the pressure differential on the further inboard turning vanes, because obviously we've dropped down the floor over here, so this is dropped down, so that we're going to be making a chunk of suction in here. Because we have dropped that floor leading edge, we've got more angle of attack on the floor leading edge, we've got closer ground proximity, it should be making more suction there. So we've increased our delta in pressure across our two edges of our turning vane. Now this should power up our turning vane vortex, which means that vortex should power up, and that will make a stronger vortex that will go downstream and should produce more suction on the floor. Obviously, it's a balancing act between making it unhealthy from overpowering it and just powering it up for extra strength. But I'd imagine that's a lot of the effect they're trying to achieve here. Now, I'm not saying that this floor detail is necessarily new for this year. It may have been on the previous year's car and I didn't see it, but that's more or less how it would work. Another detail just to note along the center line is that the secondary flick, the double T-tray as I used to call it, along the center line, the leading edge is quite close to the forward floor here. A lot of teams are running this particular detail this year, but this looks to be the closest that I've seen. And bringing this close down to the T-tray here means that the suction between these two will, generally speaking, increase for the same angle of attack, and you'll end up with a lot of mirroring effects. So you'll get more suction on the roof of this, so you'll locally generate lift on that particular lower section of the T-tray, in addition to powering up the top section. And what that can do in terms of vorticity effects is that as you increase the power on this edge, you'll increase the strength of this vortex here, and you'll decrease the strength of this vortex here. So this could be a move of biasing load from one to the other. It could also be related to how they're trying to position this vortex further downstream, because obviously if we move this down, we'll move this vorticity further down, and that may be more favorable with respect to its interactions with the main floor system. Looking at the forward floor edge treatment, you can see that we've got a bit of a gurney going on here. It's hard to tell whether that's a gurney or just a really thick trailing edge, but I'm pretty sure it's a gurney. And then it divots down, goes into another gurney along here, and then there's a discontinuity in the floor where it cuts through and cuts back. And then this ramps up again with, again, another gurney on the top of it. So these gurneys, mainly because there's a lot of outwash along here, those gurneys should convert a lot of that outwash into upwash. They should help generate more suction on the underside of this curl along here, which should help improve extraction from the floor, which will improve overall floor performance through this entire region. Now, why would you run a gurney instead of a curl? Well, if you can imagine that I've got two geometries here. If I'm looking from behind, I've basically got a curl like this, or I've got a low curl and then a gurney like that. Depending on the specifics of the flow, this curl could be too aggressive. So we've got flow going along this way from the top surface, and there'll be, at this point, flow going that way from the bottom surface. If I'm too aggressive with this curl, I'll end up with a bit of separation, a bit of loss here. That's not going to be great. If I have the same setup with the gurney, I won't get separation on this particular surface here because it's quite progressive, so I'll keep that surface clean. And then the gurney, generally speaking, creates some degree of a bound vortex on it. It can just be a slightly cleaner method than having a full-blown separation. And in this region of the car, you would expect it to be fairly effective. Now, why two gurneys instead of one? Like I've mentioned quite a few times before, we've got the advantage of discretization of any vorticity along here. And then obviously we've got the whole nature here of this is one floor ramp going up, and then we've got the discontinuity, and then we've got another floor ramp going up. This is much like the system that Red Bull ran before. And this will allow us to generate a lot of extraction in this particular region over here, which again, as per the whole intent of this region, will improve floor performance over here. Further rearwards, there's not too much to remark. If you have a look, it's got that same floor edge winglet system that we're seeing pop up all over the grid right now. If you're looking for more information on this, go and have a look at my Haas video, which will explain how this particular system works. Looking further up at the bodywork, we have a few interesting things going on. The main inlet is not really dissimilar to what Red Bull was running at the start of last year. Go and have a look at my Red Bull video if you want more information about that particular inlet. And the side pod undercut, again, is something that I've sort of covered to death here, where we've got a bit of a downwashing portion along here. We've got still a fairly smooth fillet radius around here, so that we've got not too many losses, because our flow path should be fairly straightforward and clean. And this is a feature that's common among a number of teams. So let's not go too much into what's going on here. What I do want to talk about a bit more is the top surface of the side pod, because Aston Martin has taken a few ideas from other teams here and then put their own flair on it to come up with a solution that I think is really quite nice. What I've got here is a comparison between the new Aston pods and the old Ferrari and Alpine pods, because it's kind of a hybrid of these philosophies here. You may remember some of my discussion around the Ferrari side pods last year, where I was talking about this big sausage over the top here and why you need to radius all these corners to stay compliant within the rules. And you can see that all three of these cars have had to do that. You can see that we've got radii here, and then the Alpine, which is a little bit more boxy, but you can see it's still got radius, flat, radius. Now, all these cars are doing the same sort of thing in the mid car. Basically, we've got a degree of front wheel wake that's coming along down the side of the car, and we're trying to keep it out for as long as possible. We don't want to have the front wheel wake work its way in here, because if the front wheel wake makes its way into the rear cake tin and into the lower diffuser, that is bad. So we want to keep that front wake out. So if we started to pull in the bodywork, so let's say we collapsed our side pod earlier and pull that in tight through there, what would happen is that there'd be less volume holding that wake out, so that wake would start to drift in. So all these three cars, what they do is they keep the wake out with a large side panel along the side, And so they kick that wake out at the front, they keep it out with the large side panel, and they bring it in at the last minute. The difference between the Ferrari and the Alpine is that the Ferrari keeps their side pod high the whole way up, kicks their air sort of up off the rear, and draws in their air for the rear diffuser from the bottom. What the Alpine does is that it goes and it has a ramp along here, and it draws that air from the top, ramps it down further rearwards, ramps in and draws it into the diffuser that way. Now the Aston follows a lot more this Alpine strategy, but it's a much smoother approach. If you have a look, everything is blended really nicely, so we've got a really nice path for the flow to just drop down and then work its way down to the diffuser. What you can see is that the ramp smoothly starts here, and it starts to ramp all the way down and follows this channel all the way to the top of the floor here. So from the top of the floor there, it should work its way up into the beam wing, and there'll be a bit of air that also works its way around the side to the caked in deflector and maybe even towards the rearwards portion of the diffuser. Now the rear wing stay here obviously complements this because we generate vorticity like we talked about in some of the other cars that will end up downwashing this particular ramp. So this ramp's going to have good quality attachment along there without the loss of this vorticity going in there. This vorticity should migrate its way out that way. So we should have this clean flow going down here, and then what happens is that the Aston Martin keeps its sausage as it drops low. The Alpine basically, it comes up with a fat sausage along here, and then the sausage wall then drops around here, similar to what the new Williams does. But the Aston Martin, instead of doing that, it keeps the divot with the sausage and it pulls the sausage inward. And what that would do is that the bodywork's obviously coming inwards at this point, so having that sausage going inwards will enhance the inwash going that way, and it should suppress any losses off the bodywork here where it's drawing inboard, and again, keep that central portion clean. Your trade here is obviously that by having that inwash, you're going to lose some of the power to hold the wake out because you've now got your sausage isn't as high for as long. But if you've managed to push the wake out with enough authority to start with, it shouldn't be the end of the world. So we get further back and the sausage will blend right into the diffuser top, the inboard ramp blends into the diffuser top, and then everything should have nice, good quality flow through to here. So I think that's quite a nice little solution. The other thing that I really like about it is compared to some of the other downwashing ramps that we've seen on some of the cars is that they keep their louvers up here. They've gone and they've made sure to keep this ramp as clean as possible, and their louvers there will only vent into the high central region that then goes along and exits basically on where their main cooling exit is. Now, speaking of that cooling exit, it's quite an interesting one because they seem to not mind too much about it being rather tall. So you can see it's quite a tall cooling exit there. It comes up, it's quite tall, and then obviously if they add losses from these louvers here, what's going to happen is they're going to come along and they're going to sit and essentially make the cooling losses sit somewhere around here. Now, the exit itself is very downwashing, and this is something that we've seen this year on a number of cars, is this aggressive downwash here. I explain it in my alpha video about why you would want this particular downwash here. But you can see that when you have this downwash and a very high wake profile, they obviously are quite concerned about having a tall and relatively narrow wake profile that they can then downwash. And what they're going to do is they've got their clean flow down low from the ramp that we just talked about. So there should be relatively clean flow down low. They've got their cooling losses up here. And presumably what they're doing is they're going to pass those cooling losses through the gap, thread the needle between the rear wing and the beam wing. And that is obviously what they have found to be quite efficient and effective for them in terms of producing downforce from the rear end while still having adequate cooling. So anyway, I think that's quite a neat little setup. Just a final note while we're at the rear is that I just want to point out that the diffuser uses the full legality box. Now this is something where pretty much everyone's doing this these days. Obviously at the start of last year, it was a few teams that were trying to not use the full legality box. I think it's the sort of thing where as teams get better and better control of their diffuser flows, they're all going to want to trend towards this full utilization of the legality box, because fundamentally, if the box is there, you want to be using it in one way or another. Because if you're not using it, then you are leaving diffuser expansion volume on the table, and that is going to reduce floor performance. See, in this car's case, what that means is a very aggressive flare in this particular region of the diffuser right at the end. Well, that's all for this analysis video. Thanks for watching. If you liked it, don't forget to hit that like button and subscribe to my channel for more content like this. Leave a comment below on what videos you'd like to see next, and hopefully, I'll see you next time.